So EdgeCortix is a startup that's somewhat making their debut here today. We'll be announcing for the first time some of the details of their architecture. Hamid is the director of products for their AI hardware accelerator. He's got many years previously working on FPGA-based design, PhD from Tokyo. It's interesting. Talk about how you ended up in Tokyo sometime.
Yes, yeah.
He studied reconfigurable architectures for high performance computing. The company is based in Tokyo and Singapore. So where are you joining us from?
I'm joining from California right now.
Okay, good.
Yes.
Good. Okay. Well, thanks. I'll turn it over to you. Go ahead and share your screen and you can put
Thank you for the introduction, Mike. Essentially, today I'm very excited to talk about how our AI-specific hardware accelerator IP and software solution together bring energy efficiency, reconfigurability, and scalability to AI inference at the edge. First, to give a quick background of our company, we were founded in 2019 with the mission to bring near cloud level performance under strict latency, throughput, and power constraints, especially for machine learning inference at the embedded and telco edge. We have two main locations operating out of Tokyo, Japan, and California in the US. Today, we are excited to announce our Dynamic Neural Accelerator architecture, which is a runtime reconfigurable AI processor IP series, currently available for ASICs and also being used by customers and FPGAs. Along with this, we will also present our tightly coupled compiler and software stack called MERA. To give a motivation, essentially, there are a set of very unique challenges when it comes to designing hardware for AI inference at the edge. First, a trend that we frequently see among companies working on AI chips is that they measure performance using metrics like peak tops or tops per watt. These metrics, however, do not really represent anything meaningful in practice without also taking into account the overall utilization of the chip. Moreover, power efficiency tends to be a more important metric for edge workloads compared to just pure performance. The second challenge is in terms of how we handle data. Unlike the edge, when we look at typical data center chip architectures, they tend to rely on batching to improve utilization, since in the data center, we are not really restricted to process data in the same order as they arrive. However, batching makes these chip architectures unsuitable for streaming applications at the end that need very small batch sizes, typically a batch size of 1. This also translates into lower latency being a stricter constraint than purely maximizing throughput for edge workloads. The third challenge can be defined in terms of memory usage. Most data center chips also tend to take advantage of very large amounts of on-chip memory to be able to fully cache network or model parameters. This not only increases area and cost of such designs, but also makes it extremely challenging to have the same architecture scaled down to sizes that are applicable to the edge. Alongside these challenges, among the general requirements for AI chips at the edge are adaptability to new workloads, ability to deploy multiple AI models simultaneously, while also working in a heterogeneous environment, for example, an AI-specific SoC, where there are multiple types of processors and accelerators involved. Finally, software, which is often neglected while designing AI hardware, forms the most crucial element across consumer or enterprise edge applications. We need a tightly coupled compiler and scheduler to maximize the compute utilization, and also high software robustness to support numerous types of operators, models, and machine learning frameworks. Given these unique challenges, we took a software-defined approach to AI hardware acceleration. Our approach consists of two major parts. First, on the software side, our multi-module efficient reconfigurable accelerator compiler, shortly called MERA, is tasked with efficient scheduling across the multiple compute modules that are available in our hardware architecture, minimizing on-chip to on-chip data movement, and also providing the infrastructure for early simulation and performance estimation. We also design our software in a way that optimizes the user experience of typical machine learning or AI software engineers. The second part of the solution, of course, is the Dynamic Neural Accelerator architecture itself, shortly called DNA, which is designed to be runtime reconfigurable and provide high compute utilization under strict conditions of batch one size inference, while being scalable in terms of both performance and power efficiency. Now, let's dive a bit deeper into our compiler and software stack. Our exec extends the Apache TVM deep learning compiler and provides a common interface for both FPGAs and ASICs that use our DNA IP. At the same time, we provide both high-level Python APIs and C++, low-level C++ APIs, depending on the choice of the users. One unique aspect of our software stack is that no custom quantization of any form is required. We directly support the built-in quantizers of both PyTorch and TensorFlow Lite. Any TensorFlow model can also be easily compiled by first converting it to TF-Lite. Our compiler is also capable of automatically offloading any new or unknown operators to the host CPU, which could be ARM, x86, etc. Finally, MERA provides a built-in simulator for slow but accurate performance estimation and a built-in interpreter for fast functional simulation. Our compiler and software stack are already available today, and they're being used by customers for benchmarking models and also with FPGAs. We will demonstrate this later today during our breakout session as well. Now, diving a bit further into the details of the compiler, it consists of two major parts. One part is independent of MERA, which is largely handled by the machine learning framework of choice, such as PyTorch and TensorFlow Lite, and it involves parsing the neural network alongside with calibration and quantization, which does not require any changes to the original model. This is then followed by high-level partitioning of the data flow graph using TVM's relay intermediate representation. In the second part, that's on our side of the stack, low-level graph partitioning is performed, along with target-dependent optimizations for our specific IP, which includes operator and layer fusion to reduce data movement, and tiling in different dimensions. Moreover, optimized scheduling is performed to exploit the different forms of parallelism that are available in our IP and to maximize the compute utilization. This is then followed by allocation to minimize data spills to any external memory that's attached to the IP. Now, from the point of view of a typical machine learning engineer, only three simple steps need to be taken to run a model on our DNA accelerator IP. The first step, which is completely done within the machine learning framework, is to take the pre-trained FP32 model and calibrate and quantize it to int8. Then the input resolution is specified, and the quantized model is built using a single MERA API call. At this stage, we can also specify the target for deployment, which could be our built-in interpreter or simulator, or the actual DNA hardware. It could be an FPGA or an ASIC target as well. This creates a deploy directory with the compiled artifacts, which can then be executed on the chosen target using Python or C++ applications. Now let's look at the second part of our solution, which is the hardware, and look at the lower level details of our Dynamic Neural Accelerator architecture. Our IP is specifically designed for low latency and low power batch one inference using int8 quantized data. It's also designed to be configurable and scalable, both in terms of compute and power, and support different types of parallelism, such as model, tile, channel, and filter level parallelism. One very unique aspect of our IP is its runtime memory and interconnect reconfigurability, which allows it to adapt itself to the varying parallelism of different neural networks or different layers within a network. At the same time, the IP supports interfacing external memory so that neural network support is not limited by the amount of Onchip memory available in the IP. The figure on the right in this slide shows a high-level overview of our IP, which is mainly composed of a set of convolution engines, vector engines, and the reconfigurable interconnect and memory structure, which we will discuss in more detail in the following slides. There are two main types of convolution engines available in our IP. The first one being the standard convolution engine, which is shown in the figure on the right. This engine has a data flow array-based architecture, and it takes advantage of parallelism in input and output channels, and also the filter row dimension. Each cell in the data flow array is composed of one processing element and two weight registers. The configurable parameters of the engine are the size of the data flow array and also the number of engines that are instantiated in the IP. As an example, a small configuration with one engine of 32 by 32 will provide 1.6 TOPS at the TOPS peak at 800 megahertz exclusively for standard convolution, while a large configuration such as 8 engines of 64 by 64 will provide 52 TOPS at the same frequency. The second type of dedicated convolution engine available in our IP is the Depthwise engine. It has a multiple parallel pipeline design and takes advantage of parallelism in output channel and filter row dimensions. The configurable parameters of this engine are the pipeline width, which corresponds to parallelism in filter row, the number of parallel engines, which corresponds to parallelism in output channel, and the total number of engines which are instantiated in the IP. An example configuration for this engine would be to have 4 engines of 64 3-wide pipelines, providing a maximum of 1.2 TOPS at 800 MHz exclusively for depthwise convolution. Another computational engine in our IP is the vector engine, which is composed of the pooling engine handling pooling operations, the activation engine, which implements different types of activation functions, and the scaling engine, which implements quantized up and down sampling. The configurable parameters of this engine are the number of vector engines and the number of sub-engines per vector engine. To motivate why runtime reconfigurability is required, let's consider the case of a popular deep neural network. In the encoder part of such network, early layers tend to have small channel sizes, but large row and column sizes. However, as we traverse through the network towards the later layers, the channel size increases while the row and column size decrease. And in the last layers, we typically have large channel sizes, but small row and column sizes. This structure can vary greatly from one network to another network as well. As a result, if we are dealing with a fixed hardware that only supports certain types of parallelism, we would only be able to fully utilize the compute capabilities of the chip in certain layers that match well with the supported parallelism types. The solution to this problem would be to support runtime reconfigurability in the interconnect and memory structure that would allow efficiently supporting and mixing different types of parallelism and maximizing the compute utilization of the chip. In such case, the runtime reconfiguration can happen at the granularity of a whole network or any number of layers within a network. The purpose of our reconfigurable interconnect is to allow us to change module connectivity and also adding or removing modules from the data flow at runtime. As an example, if you look at the figure on the right, when we want to take advantage of parallelism only at tile level, we configure the interconnect in a way that data flows directly from data memory to the convolution engines. And to handle the dependency that exists between the two tiles, we enable the sequencer, which ensures the convolution engines involved in the computation work in a lockstep manner. And we also use the adder that's embedded into the bottom part of the interconnect. In another example, we want to take advantage of parallelism in filter row dimension with dilation also involved. In this case, we reconfigure the interconnect so that data first flows from data memory to the line buffer and is then fed into the convolution engines in the correct order. Similarly, the adder at the bottom is enabled in this case, but the sequencer is not required anymore. Now, if we move one step forward and mix these two types of parallelism by reconfiguring the interconnect again, we would then be able to fully utilize all the different convolution engines available in the IP for this particular example. The interconnect reconfigurability in our case is implemented in a circuit switching manner with the connectivity and the points of reconfiguration being determined at compile time, but the configuration itself happening at runtime. As for the on-chip memory reconfigurability, the goal here is to have only one physical memory structure in which we virtually allocate different required memory types, and at the same time, to be able to combine consecutive memory banks to virtually create wider or deeper banks depending on the required data type size. This would be in contrast to having multiple physically separate memory structures, which would then disallow sharing unused memory space across different memory types. Directly, the on-chip memory reconfigurability leads to better utilization of the on-chip memory, and as a result, less data movement between on-chip memory and the external memory. Indirectly, this would lead to better compute utilization as well, since the memory wall will be reduced. Today, we are officially announcing the DNA IP for ASICs, which is released as a modular and configurable IP series. Typical configurations for this IP are provided as part of the DNA series, targeting different performance and power efficiency points. In a single core configuration, it ranges from 1.8 TOPS for under 0.6 watts, all the way to 54 TOPS for less than 8 watts at 800 megahertz, assuming that we are using TSMC 12 nanometer process now. Multi-core and multi-chip scalability can also be taken advantage of to achieve even higher performance if required. The figures at the bottom show typical configurations of how the DNA IP can be integrated into an ASIC. The figure on the bottom left shows a single DNA core PCIe-based accelerator. The figure in the middle shows an AI-specific system on chip, which would also include other components such as an ARM CPU or a GPU. And the figure on the right shows an example of a multi-DNA core chip, which with each chip in the core directly accessing its own external memory and an on-chip interconnect directly connecting the different cores to each other. As shown in the table on the left, the DNA series comes in 5 major performance points, with the main difference being the number of convolution engines instantiated and the amount of on-chip memory that's available in the IP. The non-exhaustive list of operators supported throughout the series include standard and depthwise convolution, stride, dilation, symmetric and asymmetric padding, max pooling, different types of activation functions, quantized up and down sampling, and so on. We are also excited to announce our forthcoming demonstrator chip using our IP. The chip is primarily designed to allow our customers to benchmark the full performance of the IP before integrating it into their own chips. The chip is currently in the tape-out process using the DNA A800 configuration with TSMC 12 nanometers at 800 megahertz. The chip will provide a peak performance of 54 inch TOPS at a total board power consumption of less than 10 watts. Both full 16x PCIe and M2 boards are planned with 2 modules of NPDDR4X running at 3,200 megahertz in both cases. Given the observed performance metrics, it's expected that the chip will be able to achieve more than 15 times better power efficiency in FPS per watt for batch 1 inference of Resident 50 compared to an NVIDIA T4. Now let's look at some performance numbers for batch 1 inference of different models across the different configurations of the DNA A series. Do remember that all these numbers are taken from standard EDA simulation of standard EDA tools. The hashed lines in these charts show the performance with the reconfigurability feature disabled, while the full lines show the performance with this feature enabled. One important takeaway from these results is that reconfigurability is crucial to be able to achieve high compute utilization and also good scalability across different performance points. Another important trend here is that smaller models like Resident 50 and MV2 SSD tend to achieve low utilization without runtime reconfigurability, and as a result, the improvement in latency for these models with reconfigurability enabled is more profound. It is noteworthy that the DNA A800 in this case achieves nearly 2,500 FPS for batch 1 inference of Resident 50 and 2,600 FPS for MV2 SSD. It also achieves over 550 FPS for object detection with the more complex YOLO V3 model using 416 by 416 resolution images. Another very important metric for IP design is area efficiency, since it directly affects the production cost. The charts here show the area efficiency measured in FPS per millimeter square. As is evident from the numbers, having the reconfigurability built into the IP has a very profound effect in improving the area efficiency, and as a direct result of improving compute utilization. Though eventually running very small neural networks on the larger configurations of the IP will result in diminishing returns. Finally, let's look at power efficiency measured in FPS per watt for the specific case of Resident 50. Apart from the obvious improvement in power efficiency with configurability enabled, we also see positive scaling of power efficiency all the way to DNA A400 with only a slight decrease when going to DNA A800. We found the power efficiency scaling to be even better for larger and more complex models in object recognition, segmentation, depth estimation, and so on. Note that in all the cases that we talk about efficiency, we should measure frames per second with a batch size of 1, since it's not really meaningful for edge applications to artificially increase the FPS using large batch sizes and as a byproduct show higher efficiency. In parallel to DNA A series for ASICs, we also provide DNAF Series IP for FPGAs, which is already being tested and used by our customers. The chart here shows the performance of DNA F200 running on a Xilinx Algo U50. As is evident, our software stack is already robust enough that it allows us to run multiple neural networks with different input resolutions on FPGAs. Moreover, to prove the performance advantage of our IP, we participated in MLPerf V1 and achieved the best performance with batch 1 inference of Resin 50 and MV2 SSD, MV2 among all FPGA submissions in the edge category across all submission rounds so far. So, to summarize, peak tops or tops over what alone cannot be used as a proxy for performance without considering utilization. And as we showed, compiler efficiency and reconfigurability are crucial to achieving high compute utilization. Our software-first approach enables us to actually realize the compute potential of our IP through efficient graph optimizations and scheduling, while also minimizing the burden of users when switching from CPUs or GPUs to our IP. In parallel, our runtime reconfigurable IP enables it to adapt itself to the varying workloads of different neural networks or different layers within a network, while also maximizing scheduling freedom and minimizing unused compute resources. Today, we officially announced the release of DNAF Series IP for ASICs. For more information, you can reach out to dna-ip at edgecortix.com. Moreover, the DNAF 200 IP for FPGAs, which was used for our MLPerf submission, is already available for testing on the Xilinx App Store using the link shown at the bottom of this slide.
Thank you, Hamid.
Sorry, I just have one extra slide.
We need to go to the Q&A now.
Yes, I just wanted to mention that we also have a breakout session at 11:10 PST with our engineers at CEO, and we will have a full demonstration of our software stack followed by Q&A, and I invite everybody to attend the breakout session. Thank you.
Great, thank you. Wow, there's a lot there. That's an impressive debut.
Yeah.
It's good always to see a startup that has the software, hardware, and results.
Yes.
At the time of their first announcement. So with announcing the IP, you're saying this is available to customers now?
Yes. So essentially the IP on the FPGAs is already available publicly. People can get a license from the Xilinx App Store. They can start using it both on Nimbix Cloud and also on premises. And for the ASICs, we're also engaging with our customers at this point in time right now.
So you said that ASIC, your test chip is coming soon.
Yes.
Like this quarter or next?
The expectation is that later this year, probably.
Okay. So sometime second half.
Yes.
Okay. So I'm wondering, as you got into describing the architecture, it's interesting. It looks like you have very fine-grained granularity in how you assign the resources to the various functions of your neural network graph. It almost first seemed like maybe there's too much granularity. It'd be hard to configure an engine unless you were designing it for one type of network. But you're pre-configuring a certain combination. Is that going to be your approach?
Typically, yes. So the thing here is that we find utilization to be the biggest problem especially for batch 1 inference at the edge. And to have good utilization, we need to have fine-grained parallelism. We need to support different types of parallelism, and we need to be able to mix these and switch across these for different layers or different networks to be able to keep the chip utilized. Again, this is completely focused on batch 1 inference. And the way things would work at runtime is that all the essentially scheduling and the points that the reconfiguration needs to happen, and essentially all the analysis that is required to determine these factors is done at compile time. And then at runtime, we essentially have instruction-based reconfigurability that, for example, at the specific layers, it changes what types of parallelisms are exploited or mixed depending on the characteristics of that specific layer or a certain number of consecutive layers. At the same time, in a multi-network environment, we would also be able to adapt the IP to the different parallelism across different types of networks as well.
Sure, yeah. We did get one question coming in here from the audience. How are the neural networks executed one layer at a time or pipeline? I think you said you did layer merging. So could you address how you actually execute the layer operations in your IP?
Yes, I mean, we can have cases where we have one layer being executed at a specific time, or if we could have cases where the network is really small, all the layers are fused together and everything fits on chip, and the whole network gets executed without any data movement, extra data movement to the host or to the external memory, for example. So all this analysis is done by the scheduler and the compiler to essentially create the best partitioning and minimize all the data movement.
Okay, you talked about utilization. That's always important. Have you measured it in some example test cases?
So we have some internal numbers, but the thing about utilization is that the numbers should be looked at comparatively, right? Especially since we are dealing with batch one performance. In a hypothetical case that, for example, we say we have 50% utilization for mobile and V2, people would think, okay, you're wasting then half of the chip. But then when you look at competitors, you'll see that they have only like 10% utilization. So at least, let's say publicly, we don't want to give exact utilization numbers. And at the same time, the software stack and the IP are also being optimized actively, so the utilizations are going up. But if a customer is, for example, interested, we can talk about the utilization numbers or what they can expect. At the end of the day, what we recommend is that if a customer, for example, has small models and they have full control on configuring the IP, we would recommend that they stick with the smaller configurations, like trying to MobileNet V2 batch one on a 50 TOPS device that really doesn't make much sense, right? But if they have, let's say, a multi-camera environment, they can have some small batch sizes, or they have a multi-network environment, then the larger batch sizes will be able to provide them with very good utilization.
Right. Yeah. I mean, 50% utilization may not be well known, but it's actually not bad. That's pretty good. Sort of the hidden secret when people talk about tops is nobody ever actually sees those tops in actual applications.
And this is essentially why in all the results we're just talking about FPS, and that's what batch one FPS.
Ultimately, frames or inferences per second per watt. That's
yes,
what we like to see. For the reconfigurability, how long does it take to reconfigure the IP?
The overhead is quite low, I would say, and this is essentially overlapped, as in passing the instructions to the chip is overlapped with the processes that are, or the computation that's already happening. So there will not be any noticeable change in the runtime, or at least considering the amount of improvement you will get because of the adaptability, the overhead will be completely negligible.
Okay, but in any case, at least the first time you configure the IP, you need some host processor to load the graph?
Certainly, yes. The host processor is required, and data has to move through essentially the external memory. The data and the instructions have to move through the external memory to get to the chip.
Right. Looking at with providing that reconfigurability, is there overhead in terms of the physical implementation, the area efficiency, or is it? Do you think it's so small that it doesn't really matter?
That's a very good question. So yes, there is some extra essentially logic involved, and also a slight increase in power, static power, as a result of that to implement or to add the reconfigurability. But the improvement that you get from the standpoint of performance is much larger than the slight increase in area efficiency. So as I also showed in the slides, you get much better area efficiency and power efficiency with the reconfigurability enabled despite the slight increase in area usage and power usage. And that's as a direct result of the improvement in utilization, significant improvement in utilization.
Well, great. We could talk for a long time, but we're out of time, and very interesting. I'm looking forward to hearing more about your progress.
Thank you very much.
Thank you for your presentation.